In this video we will take a look at semaphores. Now in the last video we have seen multi-threading and concurrency, and we have seen what can happen if multiple threads have a shared resource that has no synchronization behind it. Now we solved this problem by using MVARs and using channels, but now we want to do that with semaphores. Okay, so we have the following setup where we have two threads and one shared resource. In this case, every thread has its own control flow, and we have a scheduling so that first thread 1 goes first, then thread 2, then thread 1, and then thread 2. That's the scheduling that we will use for now. And the shared resource we will now call X. Okay, so let's assume that it has some initial value, let's say 4, and well, let's simulate this. Okay, so thread 1 goes first and saves X as a local variable Y. So Y is 4. Thread 2 does some computation and computes a Z. Now this Z, let's just set it to 1. Okay, so Y does some other calculations and calculates that Y is 5. Now thread 2 tries to get hold of the shared resource, which it can of course, and saves the shared resource as some local variable Y. Of course those two Y's are not the same. This is the local Y for thread 1, this is the local Y for thread 2. Okay, so now thread 2 has a go and does some more calculation. Now what thread 2 tries to do is the computed Z that it had before, it will now store into X. So now of course nothing changes when it comes to the values, but this 4 is now a 1. Okay, and now thread 1 does the same thing actually, and it tries to store the value of Y into X, so now it is actually 10. And now thread 2 does something. But the problem, of course, is that thread 2 thinks it successfully stored whatever the value it tried to store. So it tried to store the value 1, it tried to store the computed Z, but that is not the case, since we had a race condition here where thread 1 did some overwriting and basically deleted the result of thread 2. This is of course the trivial example of a race condition. This is a huge problem for any concurrent program, and we want to synchronize this by using a semaphore. Now, what is a semaphore? That really depends on the system and the language you're looking at. In Haskell, again, our shared resource is called X, and our semaphore here, that is just some counter that has values from 0 to infinity, basically. So in our example, we want to set the initial value of the semaphore to 1. Because how this will work, is basically the following. When a thread wants to work with the resource, it has to acquire the semaphore. This means that it basically subtracts 1 from the value of the semaphore and then does whatever it wants to do. If the value is already 0, then there is nothing to subtract, since a semaphore cannot be negative. So then we are waiting. Let's look at this in action. We will set X to 4 again. Okay, so thread 1 goes first and it acquires the lock of the semaphore. It's very important that this has to be done before we are working with the resource. So now this is not 1, this is 0. Okay, so now we set Y to X, so Y is 4. Thread 2 computes Z, let's again say that Z is 1. Now we do some calculation in thread 1 again, and now thread 2 tries to acquire the semaphore in order to, have some control flow here. But it can't, because the semaphore is 0. So now thread 2 is actually waiting. So now thread 1 is going. Again, thread 2 has to wait here. And now thread 1 can actually store its value 10 into our shared resource here. Now the important thing is that it has to release the semaphore again. So now it releases it and stores a 1 into the semaphore. Now thread 2 can go. So in this case, y is now 10 and the semaphore is 0 again. And I'm running out of space to draw here. Okay, so now, of course, thread 1 is finished in our case. So thread 2 still has to do some stuff. In this case, it does the swapping of y and z. So now it stores 1 into the shared resource. And that's about it. It releases the lock again, so it releases the semaphore again. So now the semaphore is again 1, and we're finished. Now, of course, we did some synchronization. When a thread wanted to work with the shared variable or the shared resource, it had to acquire a lock via a semaphore. And this is hugely important for multithreading. So let's look at how semaphores are implemented in Haskell. Okay, so we are in the documentation of control.concurrent. Let's look at the data types that we might use in order to have semaphores. Well, in the last video, we actually used channels and MMARs in this sense that we want to use a semaphore, but now we actually use the correct data type. So the correct data type is QSem and QSemN. QSem is a quantity semaphore. This means that it behaves just like the example that I showed, where you have some semaphore that is basically a counter that cannot go negative. Now you make a new semaphore with new QSem and you supply it an int. This means that you have to have some initial quantity. It must be at least 0. And then we have wait QSem and signal QSem. Wait QSem, of course, decrements the semaphore by 1. And signal QSem signals to the semaphore to increase the value by 1, to increment it. Of course, wait QSem is blocking. And this is very important. Now, another important thing is that there is no upper bound to the quantity of the semaphore. So it can go to, well, whatever high number you can think of. Then there is basically a sibling to this data type called QSemN. It works just like it worked before, but now wait QSem and signal QSem actually can increment or decrement by more than 1. This is very helpful if you have to, well, we will see this in a second, if you have to wait for multiple things happening. Okay, so let's look at an example. Okay, so here we are back in the code of the last episode. We want to rewrite this. Instead of MMARs and chans, we want to use QSems now. Okay, so let's think about this. We had one mutex that was giving exclusivity, mutual exclusivity, to the standard output. So how would you implement that? Well, of course, you can do it with a single QSem. So now we create a new QSem with initial quantity 0. This is very important, of course. There shouldn't be anything in the mutex, since after the creation of the threads, we want to signal that they now can start, printing something to the screen. And that's also what we want to do. What we want to do in the main is we want to signal the QSem. Okay. Or we want to signal to the mutex that it now has the quantity 1. Now it's very important, of course, that if we have a mutex, the quantity can never go over 1. It should never be 2 or 3, since then multiple threads can acquire it. So that is something that we have to make sure. There is no automatic way of doing that. Okay, so now of course we have to change our thread hello. The mvar is now a single QSem, and we have to change the functions that we used. So instead of taking something from an mvar, we now wait for the QSem, and instead of putting something back into it, what we do is we signal the QSem. And that's about it. But now the question is, how do we handle the end flags? Now, of course, our main function in the end wants to read n, units of data from this channel in order to understand that every thread has finished, since every thread signals its end with 1 unit of data in this channel. Now we can implement that with this QSemN, because waiting for the end flag, so let's just use a QSemN again with initial quantity 0, because this whole call can actually be done by waiting for the QSemN, which are our end flags, n with the quantity n. So this means that we wait until the end flags, until the semaphore end flags has the quantity n. If we start with 0 and every thread just supplies it the quantity 1, then of course we know when every thread has finished once this is n. Okay, so now we have to do some little changes to our thread function. So let's do that. And the only change we have to do here is the right chan now, of course, is a signal QSemN to the end flags with the value 1. And that's about it. Now we've rewritten our program to use semaphores. Okay, so let's test this, shall we? Of course, we have to compile it with the threaded flag. And yes, we're compiling it, we're linking it. Now we can call the program. Of course, we want to do it in a multi-threaded way. And as we can see, it is the same result that we had in the last episode. It works like a charm. But it isn't all that nice. Semaphores have a huge problem. Now, semaphores are so-called locking synchronization mechanisms. Locking because we acquire a lock for a certain resource. Sometimes this resource is the semaphore itself. This is a huge problem since you cannot really make sure automatically that you will always give some quantity to the semaphore. What if a thread is waiting on a semaphore and another thread that needs to signal to the semaphore is crashing? In this case, the semaphore will never be signaled again and every thread is blocking. So this is a very trivial example where our thread function only waits for a semaphore. And what the main IO action does is it creates an empty semaphore, then forks the thread, and then waits itself. So now both threads are simply waiting forever. Let's look at that in action. So we're compiling it, and now we can run it. And as you can see, we get an error. This is a deadlock error. Now your code should never produce this error. But now the question, of course, is how do you make sure, how do you make sure that this can never happen? And this is a very important question and also a highly debated research topic, how we can find out whether programs do not have this deadlock problem. It is an undecidable problem, so there is no automatic way of finding this out, yet we as humans can have some intuition. Now, of course, this program trivially will result in a deadlock since the semaphore is 0 anyway and there is no signaling to the semaphore, so it cannot ever not block. Okay, but there are some problems that are much more nuanced. For example, a live lock. What if two threads are in a perpetual loop that they cannot get out of because another thread simply cannot acquire the lock for a semaphore? This could happen when you're using QSemN. So please, when you're working with semaphores, make sure that you cannot have a deadlock. Well, this is all fine, and making sure that there is no deadlock, you can do that manually, of course, but it's not that easy to do. And even in production code in other languages, deadlocks can happen. In a later video, we will look at another synchronization method called software transactional memory, where we do not have this problem anymore. Okay, so if there are any questions, please feel free to leave them in the comments below. And as always, thanks for watching. You wouldn't believe how many coffees I run through making one of these videos. If you'd like to support them, you can do so on Ko-fi, where you can, well, buy me a coffee. Any support is greatly appreciated. Thank you.